Hello, welcome back to Engineers Ireland. What we're going to do is to continue on from what we covered in the last talk. We mainly dealt with two things. One was really how you prepare yourself, how you really should study in an effective and efficient way, and the other was we used indices as a kick-off point to explain to you that there are a number of items. Some are part of the Leaving Cert course, but most of them you would have been taught for Junior Cert, etc., that are really a toolbox. And like any other tradesman, a mathematician carries a toolbox. Those tools allow you to solve the mathematics that is your Leaving Cert maths. If you understand that you have a toolbox and you know that you can start to use tools, what it means is when you look at a problem, you will look to see what tool is suitable and also look at it to see what can be interpreted or simplified using some of these tools. Now, there are obviously several very good sets of books for Leaving Cert maths. The ones that I use are these ones, which are by Aidan Rowntree. Now, I happen to have a particular liking for these because I find he's very clear. I particularly like the pieces of conversation that he has through the book, not just the notes that he writes in, but his comments in between the examples are there to help you do really well. Now, I've never met the man, but he would command my respect because of how clear he can communicate his maths, and it's very obvious to me that he's interested in you learning. Now that that's out of the way, and the reason I needed to mention it is I may be talking about examples in the book, or I may make reference to certain points that are particularly in his book. We had, the last day, spoken on indices. Indices have first cousins, and they're logs. A lot of people have difficulty with logs and understanding what logs are, and in reality they're actually quite simple things. If we start off by saying a to this power or index of b produces a third number, and for example over here in the right, let's give ourselves a little opportunity. 10 cubed is 10 by 10 by 10, and that's 1,000. That's all fine if you know your base, which is this thing, and if you happen to know the index, which incidentally is also called the log. Well, if you know both of those, you can find C. Other times, the two items that you know are the base A and the final number C. So, what do you want to find then? You want to find out what power does A need to be brought to give you C. That's the job of logs. So, using those same letters there, log to this base of A of this number C has an answer B. What we are asking is, if I have this number, what power did A have to be brought to? And the answer is, it had to be brought to B. So we can say to you over here on the right hand side now, log to the base 10 of 1000 equals 3. Very handy. Logs they appear everywhere now, especially once you guys go to college and whatever it is, science or engineering, whatever faculty you're in, you will come across logs a lot. There is a small number of rules for logs. You need to know those by heart. In other words, you need to have perfect recall of them. If you want to know what perfect recall is, just ask yourself this simple question. What's 1 and 1? Well, we immediately say 2. It's recall because we didn't have to think about it. It just recalls once we hear 1 and 1. The real trick to become very fast at mathematics, and time is very important in your exam, is to have as many things available in perfect recall, because you waste no time. And also, you're not wasting any mental energy, so you're not going to get tired. You don't get tired thinking that 1 and 1 is 2. But you can get tired trying to figure out what are the rules of logs, unless you've learnt them off by heart. As my old teachers used to say, as the glán bheabhair. There was a lot of Irish in my home area, and I still do most of my, well, all my basic mathematics in Irish. Now, in dealing with logs and these type of things, we need to be aware of a few little issues. We'll just write down its rules, and the one I really want to emphasize is the last one, okay? If I have two numbers multiplied together and I get the log of it, that's exactly the same as having got the log of each of them individually and added them. This one is completely obvious in relation to the top one, because these all, as you can see, are first cousins of indices, and you can think in terms of like y to the minus 1, for example, as being the divided by y in here. So we can now say it's this one is particularly useful because in several sections in your Leaving Cert Maths, there is a need to simplify equations. I'll give you an example in a minute. Now, there's two others that are counted as rules in relation to this. One of them will tell you that log to the base a of a itself is 1. Whenever you deal with logs, always speak in your language, in most of our cases that would be English, not in mine of course. You would say, what does the base a have to be brought to give me an answer of a? Well, obviously 1, because a to the power of 1 is a. So that's pretty obvious. Now what we have to ask ourselves is log to the base a of the 1 equals 0. That's the very one that we focused on the last day, which was x to the power of 0. What is it? What is the answer to it? It's 1. So we're saying a brought to this power gives us 1. So we're just interpreting logs in terms of indices, okay? Now the one I particularly want to chat about is the one that's often put down as a fifth law, but they never seem to explain why this is useful. What are we looking at? We have a base a here, like we've been using, but look at, there's a different base here. Now, and that different base is down here. What we're saying is, if I happen to know the log to the base b of x, how do I convert that across to the log in a different base, the base of a? And that's the rule that's applied to it. Now, it's in the new log books, the new maths tables, but again, while they're very useful, you don't be wasting time flicking back and over, so you want to commit a lot of things to memory. There is a very easy way to commit this one to memory. Now, I feel I never liked the group when they came out to begin with, so I don't really like saying this. But if you look at the progression of the letters, what you get A, B, B, A. ABBA. So, if you want to remember this rule without having to go flicking through pages in the logbooks and get it out quickly, that's really all you need to remember about it. What I would like you to notice is something that has actually been the key to solving at least 3 questions in the last 10 years in the Leaving Cert Honours Maths. And if you didn't know this little thing, you would be stopped dead. You would not have been able to progress. So you would have missed out an entire part C in one of your questions. It's a very simple variation to this and an extremely useful one. What if x is equal to b? Okay? That's the question. So, well, let's put x in for b, and we'll say log to this base a of b equals. Now, we do know log to the base b of b is 1. What we're saying is, what does b need to be brought to give us 1? And the answer is 1. So we get 1 above the line. That's more useful than you can imagine. My memory tells me at the moment that there was a part C of the special question, another one in the part B of paper 2, that could be solved in about 4 lines if you knew this, and I doubt if you could have solved it at all if you couldn't do it. And I can think of 2 other questions also asked. This is not in the logbooks, so I am saying to you, commit this one to memory. It is really useful to simplify down equations that when you look at them to begin with, you think you cannot do it. One of those 3 questions had to do with summing series. And yet, what you were looking at wasn't a series. It was a multiplication of many terms. And the easy way out of it was to apply this. What else really should you commit to memory? The difference of 2 squares, I know your schools do really emphasize and push as being important. It actually solves or simplifies so many things. It is amongst, we'll say, the tools in the toolbox. It would be like the tin opener. You wouldn't want to be stuck out in the middle of, we'll say, the Canadian tundra with a whole load of tins and no tin opener. One little tin opener can open them all. The difference of squares is like that. Now, there's actually 3 equations that you need to know the answer, or that you need to know off by heart. It's the first of the 3. Now put them in this order. Put the -1 first. The reason for it is it'll help you remember the other 2, because the other 2 are quite similar and you could get confused and saying, well, is it a plus, is it a minus? If you put this one in that order, then these 2 will be pretty obvious and easy to remember. Once we have put this first one in this order, where you have the difference of squares, so you have a minus and you put in the minus term first, what you'll notice on the sum of the 2 cubes, it's a plus here. On the minus, or the difference of 2 cubes, you've got a minus. So once you get that top one in order, the other 2 should be clear to you. Now, having, for example, a plus on the outside here, you have a minus in here. Having a minus on the outside here, you have a plus in here. Now, there's a few nice little things that can come from this. It's partially a curiosity point for you, but it actually comes up in complex numbers. let y equals 1. Okay? What are we looking at there? We're now looking at let's see this piece here. If I say let x cubed minus 1 equals 0, that implies x cubed equals 1. So what do we have here? Well, if you were asked, and you can be asked in complex numbers, and it also really does come up in algebra, if you're asked what are the three roots of unity? In other words, we know that 1 is a root of unity, that 1 by 1 by 1 gives us 1. So 1 is the cube root of unity, but there's two more of them. What we're saying down here is we're saying the numbers we're hunting for, if we multiply them together 3 times, we get 1. And already in that basic equation, which is the difference of two cubes, it gives you the one factor that you know already. This one tells us, oh, x minus 1 is equal to 0, which implies x equals 1. The other two come out of the quadratic. Now, I'm just simply putting it in here to say to you that you'll be actually surprised how many times through the Leaving Cert course that you can pick on these three equations, change them only a little bit, and actually find that they are helping you, and it can help you, for example, in trigonometry or many other different sections. Now, you will find when you try to solve this here that you do get complex numbers, and straight after algebra we're going on to complex numbers, because complex numbers really are just a part of algebra, insofar as the only difference is you've got an imaginary part, not just all real bits. You will find when you read algebra and it talks about solving quadratic equations that it shies away from talking about the square roots of minus numbers. And so once we get algebra out of the way, we're going straight into complex numbers. It is a natural and obvious step, okay? So anyway, we have those three rules there. Now, this particular book I think is laid out very well, because literally only the next little section after talking about those three rules, it now starts talking about the factor theorem. The factor theorem is designed to make maths quick and easy, okay? Without the factor theorem, every time you're either looking for a factor or you are told something is a factor, you must do long division, okay? Now, the kind of long division that you can be expected to do, and I'm just taking this straight out from an example, is this stuff. And I'll just copy it straight down. Now, I always have a habit of drawing an arrow down to show me where I'm getting to. Okay, what are we doing here? We're basically saying I want to divide this thing, 2x plus 1, into 2x cubed minus x squared minus 13x minus 6. Now, there they're always smart when they write these questions. You're guaranteed that in these you will finish up taking away negative numbers. So just for the moment, before we now show you how much easier life can get when you have a factor theorem about, let's just go through what happened here. We're asking, you always ask, this number here, you don't bother with the rest of it at the moment. You say, what does it need to be multiplied by to produce that? Well, there's a 2 there, and there's an x, so it's an x squared, so we will say it's x squared. Now that x squared gets multiplied in turn into each of this and this factor. So you get 2x cubed plus x squared, and now you take away. They're equal, so you get a 0. Now you're saying I have a minus x squared. And by the way, in maths, one of the main reasons you make mistakes is while you're talking about your maths, and by the way, you do it all the time in your head when you're doing your maths, but while you're talking about your maths, if you let your English description of what you're doing get vague, you're going to make a mistake, or you're likely to make a mistake. To me, this is one area where that's very likely to happen. So let's just pick the easy one, which is the plus one, and we're saying I have a minus x squared here, and I'm going to take away a plus x squared. So the English for this is it's minus x squared minus plus x squared. Now minus by plus is a minus, so it's minus x squared, so I get a minus 2x squared. Okay, the rest moves on, and now we get down to an interesting situation. We're saying yes again, this needs to get multiplied by a minus x to give me what I have down here. So we get minus 2x squared minus x. Now look at this one. Minus 13x minus minus x. Minus minus is plus, so that's minus 13x, and that's technically a plus now. If you just think about it, you don't have to change signs along a line. Just say to yourself, it's a number minus minus a number. So that's a number plus a number. Once you have a minus here, you're saying it's this number, this long one here, minus this minus number. So minus minus is plus. That's why you finished up with a 12. Now, there's a nice amount of very basic algebra in here, but fundamentally, all of these little steps in here, that's just junior cert algebra. Now, you wouldn't want to be wasting too much of your precious time in your Leaving Cert exam on going through junior cert algebra for a very small amount of marks. So, what do you get to do? How do you deal with that? Okay, well, that's where the factor theorem comes in. It tells us something very interesting, and by the way, its proof is examinable, and it's an easy proof, and that proof uses those 3 rules that we just looked at, which is the difference of 2 squares, and similarly for the cubic ones. Okay, now it tells us a very interesting thing. This thing here, 2x plus 1, it's saying we're checking to see if it's a factor. So that means that we're saying, well, in the overall equation we're looking at here, 2x plus 1 would be 0. Now that implies that x is equal to minus a half is the root. Okay? With that factor, we get that root. What the factor theorem tells us is if I put in the root into my original equation, the 2x cubed minus x squared minus 13x minus 6, just plug in the half. If the answer is 0, that is a root. Okay? And because it's a root, the factor theorem tells us that 2x plus 1 is the factor. So let's have a peep at that for the moment. What we need to see now is, what does it mean? What does a root mean? Okay, we'll look at quadratics as well as cubics. That's a quadratic. That's another fancy name for just something that has the biggest power will be 2. Okay, A linear equation has a biggest power of 1 and a cubic has a biggest power of 3. All of these are versions of polynomials. So what we could say is y equal to this function of x, which is a x squared plus bx plus c. That being a 2 makes it a quadratic. So it's a polynomial of order 2. Okay? A cubic is a polynomial of order 3. A straight line, which is basically ax plus b, the x is only to the power of 1, that's of the order 1. So look at the thing we have drawn here. That's a quadratic. Now they'll all look like that, or they will look like this. What's the difference between both of those? This one up here, that's the way it looks when a is positive. So if this was, let's say, just x squared plus blah blah, the rest of the stuff, because x squared is really 1 plus 1 multiplied by x squared, it's going to look like that. If this was plus 17x squared, blah blah, it's always going to look like this. The upside down one, this one, happens when we've got a number here that's negative. For example, okay, minus. It's going to look like that. So, where are the roots? That's a root and that's a root. Why is it that they are roots? Well, we know as if we picked an x value over here, we would get a very big y value somewhere up here. If we picked an x value here, we'll get a negative y value. If we picked an x value over here, we're also looking at a positive value. That location here on the x-axis and that location on the x-axis, there's only two places where y equals 0. Down here the same way. There and there. Y is equal to 0. Everywhere else on these quadratic functions, when you plug in an x, everywhere else you don't get a 0 answer. That means they're not roots. So then, all real roots to quadratics, and by the same token to cubics and others, all real roots exist along the x-axis. They are when the y value is 0, and they exist along the x-axis. If we look at cubics, again there's only really two types of these things. Now this is my fancy x-axis. You'll notice it's not straight. I'll guarantee you I'm not going to lose any sleep over that. And the reason for it is your job is not to draw fancy nice little drawings in the Leaving Cert with 3 different colour pens and make sure it's neat and spend ages over it. If you do that, you're wasting time. Your job is to make the job for your mind while you're studying and while you're solving problems as simple as possible. You don't want the mind to wear itself out, having to conceptualize or keep things inside. So what you do is you put it down on paper. These drawings here, they're visual aids. They're to make life easy for you, to allow you to visualize something. So, okay, doesn't look exactly horizontal all the way through here, but I know what it is, and once I can see it, I can talk about it. So these are visual aids. You draw them quickly. Every time you draw, it isn't an exercise in taking out 3 different pens and a nice ruler and drawing straight stuff. You don't get marks for that. Well, you get a small amount of marks. You don't get much marks for it. You will definitely lose more marks because you won't have enough time if you keep doing that. So what you want are visual aids. Things that let you think and that allows an examiner see what you're up to. In this cubic, there, there, and there, they're the 3 roots. The x-axis whatever x value I pick on the x-axis, if I say what y value belongs to that, we'll just say this was 17. Well, on the x-axis, the y value is 0, of course. Anywhere else, it's 0. That means that the x-axis has an equation which is y is equal to 0. By the same token, the y-axis, which goes there, has an equation which is x equal to 0. Anywhere along the y-axis, x is 0. So what we're saying with cubics is all of its roots exist, all of its real roots exist along the x-axis. It's where the equation crosses the x-axis. Clearly, if that was 1, if I plugged x equal to 1 in here, I'll finish up with a negative y value. Okay? Now then, what can happen? That's a quadratic. It's interesting because it cuts the y-axis here. It's down below the x-axis, so it'll be a negative value there. If we look at that function, y equal to f of x, which is a x squared plus bx plus c. C is where it crosses the y-axis. What does that mean? It means that once you have a constant in your function, whether it's a cubic or a quadratic, it's telling you that when x is 0, that means that'll go to 0, that'll go to 0, y is going to be c. And if the value is anything other than 0, once there's a constant shown, it means that the function does not cross the x-axis when x is 0. So x cannot be a solution, so do not waste your time by plugging in x equal to 0 when you're hunting for roots, because you're going to waste your time. If, for example, y equals this function of x, and no constant, well, life's going to get very easy for you because you can immediately factor it. Okay? And what's it telling you? Look at this. Yep, x equal to nothing is a root. That particular one, this is where I have to get careful while I'll redraw that. Now, for example, that's one example of it. Here's another example of it. It's cutting the x-axis at the origin. Now, this particular one here has this as a solution. Okay? When x is equal to 0, it's telling us it crosses the axis. It's always easy. It's going to give you straightforward factors. You don't have to do any real thinking about it, which means they're never going to ask you that. Now, what does that mean? They'll always ask you one that'll have a constant here. So if they're going to do that, don't be stupid and waste time by trying x equal to 0. You know it's not going to be an answer. This is the free number is always going to be the value. Okay? Now, that's why the factor theorem works. It's basically saying to you, I'm looking for a factor. I could have to do a lot of long division here, but I'm giving you an option. You can appeal to the factor theorem and you plug in the root belonging to the factor and out comes an answer. The proof is a very simple one. It is examinable and you really must learn it off. The secret to it, and what makes it a simple one, is you're just going to be using the difference of two cubes, which is something you've already worked out and you've learnt off by heart because we've just looked at them, okay? And you'll also be subbing in the difference of two squares. Once you know that that's what you're going to be doing, and then you're going to use those factors, the whole thing pops out, so it's very easy. Now, I want you to see a few little things in relation to roots of equations. Remember, I mentioned the English or the language you're using while you're doing your maths is what either saves you or condemns you. When you go through this equation and learn it off, you should be saying minus b plus or minus the square root of b squared minus 4ac all over 2a. The word all is really important. If you learn that off by heart, you will always draw that line under both terms, because in reality what we have here is a minus b over 2a plus or minus So what's that equation telling us? It's telling us that the two roots have a bit in common. They'll all have this bit, the minus b over 2a, and one of them will have plus this much and the other one will have minus that much. So we can plot this. So that's the y-axis. And we're looking at this quadratic. There is an x value here. When that x value is this is minus b over 2a. Okay? And we're saying my two roots are a certain distance either side of this. We'll just call it L for the moment. Okay? We're saying L more and L less than it. This piece here, that's the L bit. Okay? So they have a common bit and they have a bit more or a bit less. Now clearly there are times when this piece here can be 0. What does that mean? That means that we have two common roots. The graph only touches at one point. Both roots are the same. When both roots are the same, their value is minus b over 2a. So, if we go back to this graph here, and we'd say, look at the graph. If we leave the x and y axis the same, but if I pushed that graph up, and literally pushed it up all the way along here, it would look like this one, just touching at one point. That one point is a situation when all of this goes to 0, and that happens obviously when the b squared minus 4ac equals nothing. What we're saying then is all of this goes to nothing, and our two roots are x equals minus b over 2a. They look like this, or and the negative equivalent of it, which is like that. Why is it that I mentioned earlier that complex numbers are very related to algebra? Over here, when we pushed that graph up, we said we brought it to the point where it's touching the x-axis and we've two common roots. If I pushed it further, like that. Now the graph doesn't touch the x-axis at all. The roots to this guy are complex. All it means is the bit in here has gone negative, and we will cover complex roots two classes from now. They're the natural step on from this, and when you realize that you're just playing algebra, okay, the exact same as you're doing in algebra, you find that you can run through the first half of complex numbers in almost no time. So the next day I just want us to finish off on algebra, and we may actually get the first half of complex numbers covered. It all depends. Well, see you guys probably in another few days. Bye now.